In this final lecture, we will look at LeChatlier's principle. As we saw in a previous lecture, we can think of chemical equilibrium as a set of scales. When we are in equilibrium, the scales are balanced. As we will find out in a future lecture, this is a state of lowest energy for our chemical system. If we change the system, then we will push the scale out of balance. The chemical system is no longer at a minimum of energy, and so it will shift the equilibrium in order to return to a minimum of energy. In this lecture, we will learn how to predict the direction in which the equilibrium will shift to counteract any changes. Its concept of shifting the position of equilibrium for a reaction is extremely important for large-scale industrial chemical processes. In order to efficiently and inexpensively generate certain chemical compounds, we have to optimize the equilibrium. Perhaps the most famous example of this is known as the Haber process for generating ammonia. Ammonia is an important precursor to agricultural fertilizers. The reaction of interest, N2 gas plus 3H2 gas, forming 2-ammonia gas, is not particularly favorable at normal temperature and pressures. It was discovered that by adjusting the temperature and the pressure of the reaction, the yield of ammonia can be greatly increased. Haber and his co-workers discovered that there was a specific temperature and pressure combination that maximizes the percent yield of ammonia. This figure demonstrates the percent yield of ammonia as a function of temperature and pressure. The temperature axis in the front ranges from 400 degrees Celsius on the left-hand side up to 550 degrees Celsius on the right-hand side. The pressure axis on the side ranges from 200 atmospheres in front to 500 atmospheres in the back. Each block represents the percent yield of ammonia at that pair of conditions. Notice that the largest percent yield of ammonia occurs at the temperature of 400 degrees Celsius and a pressure of 500 atmospheres. If we decrease the pressure, we see that the percent yield of ammonia decreases. Likewise, if we increase the temperature, the percent yield of ammonia decreases. Using LeChatlier's principle, we will be able to predict both of these trends. The ability to predict in which direction a chemical equilibrium will shift when changes are made is due to what is known as LeChatlier's principle. LeChatlier's principle can be stated as follows. If a system in equilibrium is perturbed by a change in one of the following: reactant or product concentration, pressure, or temperature, then the system will shift the equilibrium position so as to counteract the effect of the perturbation. In other words, if we make a change to our chemical system, it will respond in such a way as to minimize the effect of the change that you've made. We are going to look at all three of these possible changes. First, we will consider a change in concentration for one reactant or product. If we increase the concentration or partial pressure of a reactant or a product, then the system is now unbalanced on that side of the reaction. Consequently, the system will react off the excess by shifting to the opposite side of the reaction. There are four possible realizations of this idea. First, let's increase the concentration or partial pressure of one reactant. In this chemical system, we have both the blue and the red reactants forming the green product. In this case, we increase the amount of the red reactant. Notice that this overbalances the scales on the side of reactants. In order to return to balance, we have to react off some of our reactants, forming more of our product. Once we do this, we have returned to equilibrium. Thus, increasing an amount of one reactant will result in a shift toward products. Now we can increase the concentration or partial pressure of one product. In this case, we are increasing the amount of our green product. By doing so, we're overweighing our balance on the product side. In order to return to balance, we now have to react off some of the excess product, forming additional reactants. As a consequence, increasing the amount of one product will result in a shift toward reactants. Now let's consider what happens when we decrease the concentration or partial pressure of one reactant. In this case, we have decreased the amount of the red reactant. This now causes the reactant side to be deficient. In order to replace this, the reaction must back-react, consuming some product and forming more reactants. Thus, decreasing the amount of one reactant will result in a shift toward reactants. Lastly, we can consider what happens when we decrease the concentration of one of our products. In this case, we have decreased the amount of our green product, thus causing a deficit on the product side. In order to restore balance, we must now react in the forward direction, consuming some reactants and replacing the missing product. Consequently, decreasing the amount of one product will result in a shift toward products. As an example, let's consider the reaction H2 gas plus I2 gas forming 2HI gas. First, state two ways to increase the amount of HI in the system. Firstly, we can increase the amount of H2. This will overbalance the reactant side, requiring us to react toward products and shifting the equilibrium toward HI. Likewise, we can increase the amount of I2. This will have the same effect of shifting the equilibrium toward HI. Now let's state two ways to increase the amount of H2 in the system. First, we can increase the amount of HI, thus overbalancing the product side. This will cause a back reaction toward reactants and shift the equilibrium toward H2. The second way is that we can decrease the amount of I2, thus causing a deficit on the reactant side. This will cause a shift toward H2 as well. Now let's look at the effect of changing the pressure of a gaseous system. There are three ways in which we can change the pressure of a gaseous system. First, we can either increase or decrease the partial pressure of a reactant or a product. This will change the overall total pressure for our system. Secondly, we can change the volume of the system by either increasing the volume or decreasing the volume. Thirdly, we can add in an inert gas, which will cause the total pressure to increase. The response that the system makes to each of these is different, but we will be able to predict the direction of the shift in equilibrium for each case. Let's start by considering changing the partial pressure of one reactant or a product. It turns out that changing the partial pressure of a reactant or a product is equivalent to changing the concentrations. This is just what we did in the previous section, and the results mirror that section. By increasing the partial pressure of a reactant, we will shift the system toward products. By increasing the partial pressure of a product, we will shift the system toward reactants. By decreasing the partial pressure of a reactant, we will shift the system toward reactants. And lastly, by decreasing the partial pressure of a product, we will shift the system toward products. As an example, let's consider the reaction of nitric oxide gas plus bromine gas, forming NOBr2 gas. To increase the amount of products, we can increase the partial pressure of either nitric oxide or bromine. Either of these will cause an excess of reactants, which must be reacted off. The equilibrium will then shift toward products. Now let's consider changes in the volume of the system. Changing the volume of the container of gases will change the pressures. Recall from the ideal gas law that the volume and the pressure of a gas are inversely proportional. As a result, if we increase the volume of a gas, we cause the pressure to decrease. Conversely, if we decrease the volume, we cause the pressure to increase. The system will respond based on the number of moles of gas molecules present. At a higher pressure, the system wants to react off gas molecules in order to lower the pressure. At lower pressure, the system wants to form more gas molecules in order to fill the deficit. As a result, if we increase the volume of our system, we will shift the equilibrium to whichever side, reactants or products, that has the greater number of moles of gas. Likewise, decreasing the volume will shift the equilibrium to the side with the fewer number of moles of gas. Let's return to the Haber process. The chemical equation is nitrogen gas plus 3 hydrogen gas forming 2 ammonia gas. Recall from earlier in the lecture that the yield of ammonia was greater at higher pressure. Looking at the chemical equation, we see that we have 4 moles of gas on the reactant side, 1 mole of nitrogen, and 3 moles of hydrogen. The product side has only 2 moles of gas, or 2 moles of ammonia. Thus, by decreasing the volume of the reaction, we will increase the pressure. This causes the system to shift to the side with fewer moles of gas. In this case, the equilibrium shifts to produce more ammonia because of the fewer moles of gas on the product side. Now let's consider what happens if we add an inert gas to our system. If we pump an inert gas, such as neon or argon, into a closed container of other gases, this will cause an increase in the total pressure of the system. However, if the inert gas is not a reactant or a product, then this does not change the partial pressures of either reactants or products. As a consequence, adding an inert gas that is not part of the reaction will have no effect on the position of the equilibrium. Returning to the Haber process, if we add in some argon gas, this will not cause any shift in the equilibrium because it does not take part in the reaction or in the equilibrium expression. Lastly, we can consider the effect of changing temperatures. The effect of temperature changes is a bit more subtle. To this point, all of the changes we have discussed occur without altering the equilibrium constant value. The ratio of concentrations stays the same, even though the individual concentrations change in order to maintain that value. When we change the temperature of a system, however, we almost always change the value of the equilibrium constant. This effect arises through what is known as the Van't Hoff equation. The results of the Van't Hoff equation are as follows. For an endothermic reaction, one in which delta H is greater than 0, increasing the temperature results in an increase in the value of K. For an exothermic reaction, where delta H is less than 0, increasing the temperature results in a decrease in the value of K. The opposite is also true. Decreasing the temperature for an endothermic reaction decreases the value of K. Decreasing the temperature for an exothermic reaction increases the value of K. From a practical point of view, we approach this in a slightly different way. An endothermic reaction requires heat energy to proceed, and therefore we treat heat as a reactant. By increasing the temperature, we are adding in heat energy. This is effectively increasing the amount of a reactant, and this shifts the equilibrium toward products. This is the same as saying that K gets larger. By decreasing the temperature, we are removing heat energy, effectively decreasing the reactant amount. Thus, the equilibrium will back react to shift to reactants. This is the same as saying K gets smaller. An exothermic reaction releases heat as it proceeds, and therefore we treat heat as a product. By increasing the temperature, we are adding in heat energy, thus effectively increasing the amount of products. This causes the equilibrium to shift back to reactants. This is equivalent to saying that K is getting smaller. By decreasing the temperature, we are removing heat energy, effectively decreasing the amount of a product. This causes the equilibrium to shift toward products. Equivalently, this is the same as saying K gets larger. In our final example, we return once again to the Haber process. The change in enthalpy for this reaction is negative 91.8 kilojoules per mole. Recall from earlier in the lecture that the yield of ammonia increases as the temperature is lowered. This reaction is exothermic. Delta H is less than 0. This means that we treat heat as a product. If we increase the temperature, we are increasing the amount of a product, and the equilibrium will shift backwards toward reactants. If we lower the temperature, we are decreasing the amount of a product, and the equilibrium will shift towards products, thus increasing our yield of ammonia at lower temperatures. We have now concluded the discussion of LeChatlier's principle, the last lecture in our chapter on equilibrium chemistry. In closing, if you think of your reaction as a set of scales, you can predict the direction in which an equilibrium will shift to counteract a perturbation. By increasing a reactant or decreasing a product, the system will shift toward products. By decreasing a reactant or increasing a product, the system will shift toward reactants. We can treat this either as a concentration of reactants or products, or as a partial pressure. The effect is the same. Likewise, we can treat heat energy as a product or a reactant. Increasing the volume of a gas system will shift toward the side with greater moles of gas. The opposite is also true. Decreasing the volume will cause a shift toward the side with fewer moles of gas. Lastly, don't ignore the fact that changing the temperature actually causes the value of K to change.